Fantastic. Thank you. Right. Oh, share my screen. Thank you so much for the fantastic introduction there, and thank you all for inviting me. I absolutely jumped at the opportunity to come here, hence why I'm here fresh-faced, and give me an hour or so and I'll be curled up in the corner asleep, I'm sure, just purely from the jet lag. But let me share my screen here. So if I can just get a nod that I've done that correctly. I'm going to assume that's coming through. So I'm here this evening to... Oh, all right. Here we go. Let's try that. Yeah, I'm from a company called DiffBlue. So we're based in Oxford in the UK. We are a spin out of the Oxford University Computer Science Department back in 2016. And we use reinforcement learning to write unit tests for Java. And that's reinforcement learning as opposed to large language models that I'm sure we're all saturated this last 12 months hearing about. But reinforcement learning is a different technique. And what I'm going to be taking you through today is a bit more about the differences between those. Yes, our product is, but the talk I'm going to be a bit of everywhere, even a little bit of assembly in this. So just to keep you all on your toes. So yeah, I came to DiffBlue from Cisco because I realized my time at Cisco, I learned how powerful unit testing is, allowing us to build great software and move quickly. But I also learned how hard it is to do unit testing well and do it at scale. And then I came to DiffBlue because it was like, what, you can write unit tests thousands of times faster than a human? That's got to be something exciting to move into. So my talk this evening is going to be about the differences between large language models and reinforcement learning, in particular. Sorry, move this out of the way here. In particular, in terms of writing code. So when we look at generative AI for code, we've got these two camps. We've got the large language model based tools such as GitHub Copilot, Tab9, ChatGPT. And then on the other side, we've got ourselves and an open source project called EvoSuite that use reinforcement learning to write unit tests. So before we get started, can I have a show of hands from the room here? Has anyone tried using any sort of AI tool to help them with their coding? Then if you could keep your hand up if you're still using that tool for coding and if it's become part of your workflow. So a couple of hands have dropped there, and that's quite typical. There's a lot of potential in AI as a whole for helping us code. And there's a lot of promise there, and there's some obvious wins. But is it at the point where it fits seamlessly into our workflow? Not yet, especially with the LLM models, but it's getting there. And it's just interesting to see. I think we've all tried it, or we've all been aware of it, but how many of us are actually using these tools day to day? On the left-hand side here, is certainly not where it could be. So let's have a look at what we're going to learn. So by the end of this session, we're going to have a good understanding of a quick overview again of large language models and transformers in particular, and jumping into looking at the strengths of large language models for coding tasks and some of their weaknesses. Then we're going to look at reinforcement learning. We're going to look at how reinforcement learning is used to play games, and in particular, a couple of examples using Go and some of the work from Google, which is really exciting. And then I'm going to do the live demo, and I'm going to show you what you can do using reinforcement learning. If you've got any questions, if you could just hold on to them until the end. I'm going to cover probably most questions by the time we get to the end of the talk, but any questions I'd be happy to answer at the end. So let's start with large language models. So a lot of this is going to be a recap. ChatGPT is cool. I think we all know it's pretty cool. I asked it to write me a haiku about an Englishman in New York. This should be easy, given that there's a huge amount of source content. Sting literally wrote a song on this subject. And this is what it came up with. And I think that's a pretty good haiku. And it's definitely tea in a coffee town. This shows what ChatGPT and large language models are really good at, and they're really good at making stuff up. So they're good for language tasks. They're built for language tasks at the end of the day, and they are very, very good at that. In particular, writing new content, new copyright for copy content for use in a whole range of different disciplines. But of course, LLMs like ChatGPT can also write code. So let's just quickly recap transformers. So transformers are the core technology used in large language models. So the transformer was invented at Google, where it originally developed for working with text and for things like language translation. So you can see an example here of translating from English to French. So the transformer breaks down the input into what it calls tokens. These are kind of an analog to words, not quite, but it's enough for this example here. It breaks it down into those tokens, and the transformer's trained on a collection, a corpus of input, which is a bunch of, in this case, English sentences and the equivalent French sentences. And it is looking at the statistical patterns that link those sentences. So it does this by trying to understand, and every time I say understand, I'm going to put it in air quotes, but it understands what role the word plays in the text. So is it an adjective, is it a verb, is it a noun, and so on. And it's that information and that context about the word that we get out of the transformer the next word. We take that context and that word and the input and put it back into the transformer, and then we get the next word. So we're taking our output, we're putting it back into the transformer with the original input, and it's telling us what the next word is. So transformers are iterative, and they are really just giving us what is the next word. So prediction engines for telling us what the next word in the sequence should be. So here's the story so far of GPT. So generative pre-trained transformers. So this is a series of models from OpenAI, as I'm sure you're all aware. GPT-2 was an open source model back in February 2019, mainly designed to summarize and translate and answer questions about text. GPT-3 is a much larger model. So we've gone from 1.5 billion parameters to 175 billion parameters. And a parameter is a value inside the model that changes as the model is trained. So the quantity of parameters is a proxy for the intelligence of the size of the model, but the intelligence of the model. So the really interesting thing about GPT-3 is it can actually do things that it wasn't trained to do. And that's really exciting in of itself. There's a derivative model of GPT-3 called Codex, which is used in GitHub Copilot, used for code completion. So that's trained on text and code. So it's a smaller model. It's more specific to the job of code completion. And then there's GPT-4 that is rather new. We know less about how GPT-4 works. OpenAI have really trying to make themselves a commercially successful company now. And so we think that they're keeping some of their secret sauce close to their chest, and that's why we know less about it. But we believe it's probably got about 1.76 trillion parameters. The thing with GPT-4, which is particularly interesting as well, is its ability to take images as input and to create images and to use derive information from an image. So you can give GPT-4 a picture of a graph, we can give it some visual data, and it will turn that into text, and then it can use that as prompt input. And then it can take text and it can turn that into prompt output. So you can go from one picture to another via text. But we can see at the bottom there that a real focus for GPT-4 has been on safety. I think they learned a lot from GPT-3. Really, the problems with large language models is they can just be wrong, and they can spout really dangerous garbage that we need to stop them doing. They can make up things, they hallucinate, etc. So a lot of time and effort has been put into mitigating this bias. So let's have a look at some examples of using GPT for code creation. So here I've asked GPT-4 to write me the code to call the Twitter API. So that's quite an open-ended request, quite broad, just write me a request to the Twitter API. And here's a great example of what LLMs can do. It saved me the time of Googling around to find the code example. And it's given me some pretty good code. And this code is actually going to print out the tweet in my timeline. So this is impressive. It has saved me the time of Googling and reading documentation and copy and pasting that into my IDE. So to really demonstrate how LLMs think about the world, let's give it a semantically identical request, but let's use different language. Let's ask it to give me the same for the X API. So we all know that Twitter is now X. And we can guess that the API is probably the same. I'm pretty sure it's not changed under the hood. But the LLM has far more training data and far more knowledge on Twitter than it does on X. So what it's actually given us here is a far more generic API call. And it's a good generic API call here. It's lost all that context, though, of tweets and Twitter and timelines and things. So it's got no model of how the world works. It has no way to deduce that the identity of Twitter and X is the same thing, and something that would be very easy for us. So it's using the language as the input, and the language has led it to believe that I'm asking for something completely different. So at the end of the day, it's really giving us what it thinks is most statistically pleasing. But in this case, it just didn't have enough statistics to tell us the right answer. So let's have a look at unit test writing. So this is a great example because now we're using code as part of that prompt. We're not just asking it we're not just asking it to write us some code. We're giving it some code and asking it to do something with it. And this is where we see more about that idea of the lack of a model of code and of in this case, Java. So here we've got a Java method called add, and we give this code to the LLM along with a request for it to write a unit test for this add method. So the LLM gives us a perfectly valid, albeit verbose unit test for an add method. It looks pretty good. But that method doesn't add anything. There's no body to that method. It has no concept of the code, the structure of the code, what might be missing from the code. Is it good code, bad code, valid code? It has been led astray by the fact that we've asked for a test for an add method, and it's given us a good unit test, but which is absolutely in no way related to the code itself. So let's extend this. Let's give it a method body. So now we're asking it to write a unit test for this add method that returns a multiply by b. And two things interesting to observe here. It's given us a different unit test. This is less verbose. This is a more human-like unit test, but it's still giving us a unit test for an add method. So it's given us a different unit test. So something has changed, but it is still for an add method. So let's go one step further. Let's give it a more complex piece of code. So here, this is where it really starts to lose the plot. We've given it a saturating add function here, so an add function that is bound to between -100 and 100. And it returns what looks like a really good unit test for assertions here. And as the complexity of our prompt has increased, though, it started to really hallucinate the need for this date time service object thing for some reason. No idea why. It's seen that somewhere, obviously, and it's decided that that's necessary. And if that wasn't there, we'd be really impressed by it. But it's now starting to step towards the realms of being frustrating for us as developers, because now we have to go back and examine the code and understand, is it doing what it should be doing? So how are we going to combat this lack of safety and correctness with LLM responses? So we use good old human beings. So in the case of GPT-3, there's a reinforcement learning model in front of the LLM, between us and that LLM. And it's used to weight the responses to try and avoid some of this lack of correctness and to stop it spewing offensive garbage. So in this example, we give it the prompt, Citizen Kane is ... and GPT-3 comes back with 4 possible answers. So one of the greatest movies ever made, a commercial failure. It was a commercial failure. The end of Orson Welles' Hollywood career, or a vicious and irresponsible attack on a great man. So humans there would rank these responses, and that is the mechanism used to protect us as the public using this from getting the wrong answer, getting hallucinations, and getting given information which is not nice output to see from a tool like this. But we are now using humans to manually correct the information. So the net is, it's all about the text. It's about the text in the prompt and the training. Prompt engineering was mentioned earlier. There is no such thing as prompt engineering. It's trial and error. If it was engineering, we'd be able to be very precise with this, but it's not. It is pure trial and error. They don't understand. They just learn text patterns. There is no deduction here. We can see the lack of logic as well by asking an LM to do multiple digit math, something that we would say a small child should be able to do quite easily, but an LLM we then assume should also be able to do it, but it struggles because it's looking at the language, it's looking at the words, it has no concept of the world of maths at all. And it starts to lose the plot when the training is thin. An important thing for a lot of customers of ours who have their own proprietary frameworks and libraries, an LLM will never produce code that will call those frameworks or libraries because there's nobody trained on them. And these are problems the same regardless of the model size. So what's the alternative? Reinforcement learning, aka trial and error. So Jeff Hinton, one of the founding fathers of AI, said himself, we learn how to throw a basketball so that it goes through a hoop. We don't learn that using language at all. We learn it through trial and error. So we can see the chap on the left is sat there reading his book about how to play basketball, and the two on the right are playing basketball. If we give them all an hour, and then at the end of the hour, we say, right, we're going to have a competition. Who's going to shoot the most hoops successfully? My money's on the folks on the right-hand side. So we treat problems like a game in reinforcement learning. So let's have a look at the game of Go. So we have a set of rules for the game of Go. The game of Go is believed to be far older than chess by about 500 years, we think. It's much harder than chess for several reasons. And it's really because the search space is just so much bigger. So the search space for chess is about 10 to the 50. In the case of Go, it's 10 to the 170, an unfathomably large number. It may as well be infinite. In chess, we can prune that space, and Deep Blue, IBM's chess playing game engine, is good at chess because it prunes the space and it uses custom ASICs to brute force the board. And that's easier because we can evaluate moves in chess, the value of those moves much better. Chess pieces have different weightings of their value, etc. It just does not work for Go, the brute force method. And also long-term strategy can make a huge difference in Go versus optimizing for short-term, just capturing as many stones as you can. So winning at Go cannot be brute force, and it cannot be taught. So AlphaGo from Google uses probabilistic search to identify areas of the board where solutions are likely to exist and focus on those. So we're spending more time looking where the solution is likely to be, rather than just looking everywhere. And we use the rules of the game to bound the problem, and our understanding of penalty and reward from the game to guide our search. So although the search space may as well be infinite, we have rules that help guide us. So let's look at another piece of research out the same group at Google, a bit closer to home. We're going to have a look at the Google AlphaDev sorting solution. So this is a sorting algorithm optimization that came out of Google AlphaDev. They wanted to optimize code, and they said, we're going to start with assembly because it's the rawest form of code that we can try and optimize. Let's try and optimize sorts, because sorts are used everywhere. The speed of a sort function is critical when it comes to a lot of mathematical operations. And there are trillions of times a day sort functions are called within code globally. If we can make it more efficient, that's a great thing. So on the left, we have what we thought of as a state-of-the-art sort3 function. So a function that takes in 3 inputs, A, B, and C, and sorts them. Sort functions obviously go up from there to sort hundreds, thousands, millions of numbers, but let's start with the basics. So the assembly for this has 18 instructions. This is the pseudocode here for that. When they asked reinforcement learning to come up with a better sort function from scratch, it produced a 17 instruction version, so 1 instruction less. And we can see here that there's 1 fewer comparisons made. So instead of down here, we can see we're comparing A, B, and C. We actually found we don't need to compare C. And that's because from a previous step, we already know that B is already less than C, so we don't need to compare them. So that optimization has done 2 things for us. It's number 1, actually made the code quicker, we're using less CPU cycles, but it's also provoked us as a field, really, to think differently about code optimizations. And if this is possible, what else is possible? And so they actually found this works all the way up. Sort 1, 2, 3, 4, 5, all the way up. This optimization works. And at sort 8, there is actually another trick that they found, and that works all the way up. So reinforcement learning has helped them to discover a better way for sorting numbers. So the logic here really is that at the point that you're doing that second set of comparisons, you've already done the first comparison between B and C, so you don't need to do it again. Something that might seem quite trivial to us, but it's something that hasn't changed for a long time. So much so that when they realized the power of this, they engineered this back into C++ and actually got it built into the LLVM C++ sorting library that hadn't been updated for 10 years. And that's now standard. So that's how amazing this is. It's not that obvious because 10 years that library had stood still. So the way it does this is uses a classic reinforcement loop here. So essentially, the alpha dev reinforcement learning starts with some assembly code, and it runs a sort function given some inputs, and it measures the execution time of that and whether it got the right answer. So we evaluate the effectiveness of that sort function, that first candidate sort function. So we know what the expected output is, we know what the actual output is, and we see how good was it at getting that expected output. And we use that understanding of what good looks like to change the assembly code and try something different. So essentially, we're trying to shoot the hoop a slightly different way the second time. So we change the assembly code, we evaluate the effectiveness of that assembly code, we use the reward or the penalty to guide us towards better and better code, and we end up with that better sort function. So a classic reinforcement learning algorithm here running to solve a very specific problem by trial and error. So consistently, accurately writing tests is much harder than code completion. So code completion, like GitHub, Copilot, etc., use the current file for input. There's a limited amount of input you can give to a large language model. We can't give it information about the rest of the application, the imports, etc. And GitHub states that Copilots write exactly 43% of the time with Python. And the biggest problem with that, though, is your computer doesn't know when it's right. It's right 43% of the time, but we don't know which ones are right. We have to check that ourselves as humans. Language predictors don't understand anything other than the text we've given it. They're not applying maths and logic and all those other things that we mentioned. So what we need is a model of the program. We need that context. We need the rules, just like with the alpha dev example there, we need to understand, what does Java look like? What are the rules of Java? What are the rules of the unit testing game? What does good look like? How do we know when we're getting closer to shooting balls in hoops? So, and then AI code automation is valuable when it's autonomous. A lot of people dropped their hand earlier when I asked the question, are you still using these tools? And it's the fact, for me at least, that I just don't trust tools. I'm having to check the output. It's not saving me the time. When it can be completely autonomous and you don't have to check the output, it just works. That's when AI for code is most valuable. So let's have a look at using reinforcement learning for writing unit tests then. So the search space is much like Go. It tends to be n search space. It may as well be infinite. There are infinite Java, near infinite number of Java applications out there, and therefore near infinite number of unit tests. So we approach it like a game. We know the rules of Java. We know what good Java looks like. We have a syntax to follow. We have to satisfy a compiler. And we use that to guide us to find that correct unit test. We also have other clues from the environment, the dependencies, even the version of the dependencies, the literals in the code, the factories, the dependent classes, etc. We use a lot of information to guide our search. So if we were to look at it on a Venn diagram, we know that we need to take the entire set of possible unit tests and narrow it down to tests that are valid and actually compile and run. We need to know that the unit test we're writing produces good, high quality coverage. So unit tests that can catch regressions. And they've got to be unit tests that look human-like. It's got to be unit tests that a developer can look at after it's failed and read it and understand what's gone wrong. It can't look like it was written by a machine. So we use this to guide our search to help us understand if we're getting further away or closer to writing unit tests. So the DiffBlue reinforcement learning algorithm looks like this. So we start off with writing an initial candidate test, and that's using those clues that we've detected so far. We run that candidate test, and that's essentially shooting our first basketball, trying to get it in the hoop. And we see how far from the hoop we got. So we look at the results, we see how it does, we look at how much coverage it got, we look at how human-like it is, we look at some other things that are a bit of our secret sauce. And we're essentially evaluating how effective the unit test is, and we use those measures to predict a better unit test. So we adjust our technique. We write a different unit test and we shoot that second hoop. We do that hundreds and hundreds and thousands of times until we get the right unit test. So we can do that per method. We end up with all the unit tests for a method, and then we can do that for an entire million-line code base and give you 100,000 unit tests that describe the current behavior of the code. So that, if we have a look at that in terms of a CI pipeline, so this is sort of the GitHub view of the world with pull requests. Here you've got your code on the left, you've got your handwritten unit test, and you come along and you make a code change. So you change your code, you update the unit tests, you add some new unit tests, you might delete some unit tests, you kick off a pull request. We run those unit tests in our CI, and we use the results to tell us, did we have a regression? So has the code behavior that existed before my code changed? We've got to protect ourselves from making our existing code worse, or have I introduced a new bug in a new piece of functionality, or is everything good and it just passes? So what we can do with reinforcement learning written unit tests is we can produce that initial baseline set of tests, 100,000 unit tests for your application, and that's protecting the current behavior of your code. Those tests describe the code before you make your code change. So now you make your code change and you can kick off your pull request. We still run the manual unit tests that you have, but we're going to run those DiffBlue unit tests that were written before your code change. And any failing tests are going to tell you about how the behavior of your application has changed. So if you've got new unit tests from DiffBlue, that means that you've introduced new behavior, and the unit tests tell you exactly what that new behavior is. If we've deleted a unit test, that tells you that that behavior no longer exists. If we update a unit test, we tell you how you've changed the behavior of your code. So unit tests here are telling you the behavioral change within your application. So now when you do your code review, spotting is it a regression or a bug, or is my code good? Validating that your code is behaving as expected is much easier. So let's have a look at this in with some code. So I'm going to jump over here to Safari, and I'm going to pitch myself around here a little bit. So here we've got Spring Pet Clinic. So I'm sure you've all seen Spring Pet Clinic, the demonstration application from Spring. A veterinary surgery management system, so it has owners, pets, vets, and we have a Spring application with, if I can find my mouse, there we go. So we have a find owners form. So this form has 4 different behaviors. So first of all, if I don't put in a name and I just search, I get a nice paginated list of responses. If I search for a name for which there are multiple owners with that same name, so Davis, it's going to return just those users, just those owners, sorry. If I search for a name where we know there's only one of them, so McTavish, this takes us, it skips that search results list because there's only one owner. It takes us straight to the result. And if we search for someone who isn't in this, my cat doesn't use this veterinary surgery, so I'm not in there, not found. So there's 4 cases there that we want to write unit tests for. So bring you over here to the terminal where I'm going to run diff blue cover. So we're running this against that class. And what we're doing is we're discovering the context of the environment, first of all. We're understanding what simple things like what version of Java are you using, what's your build system, what dependencies do you use, what versions of those dependencies, and that's all really important so that we write unit tests using the same versions of things that you've used in the same way as you've done it. So it's working its way through that, and it's going to start writing the unit tests for this class, and it's going to use that reinforcement learning to do that. It's going to work through each method one by one. It's going to take that method. It's going to take the actual bytecode for that method, and it's going to put the bytecode for that method into our reinforcement learning model, and we're going to trial and error. We're going to shoot basketballs against that code until we get unit tests. So you can see here there's 10 callable methods inside that class, and we're writing unit tests for it. So what we're, I'm going to let that run. I'm going to nip back and I'm going to show you the code for that form. So we have the 4 pathways through that code. So we've got the empty fields pathway at the top. We've got the not found. We've got exactly 1 result, and then we've got the 2 or more results. So these are the 4 pathways for which we want to actually write unit tests for. And we can see there that we've written 14 unit tests for that whole class. And what we're doing at the end here is we're now actually running those unit tests. So we're making sure that they compile, and we make sure they run, and we make sure that they pass. And that's our validation for being able to say autonomously we've written that code. So going to jump to IntelliJ here to show you the actual unit test it's created, just nicer format to show you in here. So this here is the test class we just wrote, and we're going to take you down to, here you go, test process find form. So there's 4 unit tests here. We've got test process find form 2, 3, and 4. And we can see here that we are, for this first case, where we're going to return an empty list because this is testing the no owner found. We're creating the mock data, and then we're using mock MVC to mock the response, which is just going to take us back to that find owners form, and there's going to be a message saying no owners found. You see a second example here where we've built a mock object for an owner. And in this case, we're testing that that 1 owner is found and returned. in the, and we actually see down here that when we do this, we see this is now redirecting us directly to that owner record. We're not going via the search results. The next one here, we've created two mock objects because this is testing that there's two found. So we're going to show the search results with those two records shown. And then finally here, we're searching for a user here, the end there, Joe, who doesn't exist. And we're going to return that to say that that user doesn't exist. So what we can see there is that we've written complete code that is ready to go because we've used the rules of the game in the context, and we've repeated through that cycle of trying to find what the right unit test is, rather than looking statistically for what might be the most pleasing unit test. So LLMs are really great at what they do, which is process language and deal with creating new things in the world, in the domain of language and words. But that is also their biggest weakness. They can't use that to handle logic, can't use that in anything with a complex model such as code or Java, because they have no concept of what the model of the world looks like. Reinforcement learning writes code autonomously by playing the game, not just reading about it. So it's much better than large language models when it comes to unit test writing. And AI for code is the future when we have the context of your environment and we understand what good looks like, and we have a model that can use those to write good unit tests. So I hope that was interesting, and I hope you learned something. Got two suggestions straight off the bat. Number one, if you're interested, the work from Alpha Dev was published in Nature, which is absolutely fantastic. Go read that paper. It's so exciting about how they've used the reinforcement learning to solve some really cool code optimization problems. There's a group of fantastic interviews with the team as well. Go try GPT-4. Again, absolutely fantastic. I'd be lying if I didn't admit that I'd used it to help me write some of the content for today. It is a really, really exciting tool. I really love the image support. And if you want to give us a go, you can try us out, both our CLI version that you saw there, and we have an IntelliJ plugin as well. So yeah, thank you for your time, and thanks for giving me the privilege of being here. I know you've all given up your evening to hear me talk. And if you've got any questions, I'll be happy to answer them. Thank you.
First of all, thank you for the great talk. Quick question: when you talk about high quality unit tests, how do you measure the quality? For example, if I were, one quality metric is running mutation testing frameworks like PI test. So if I were to run it on, let's say, that code example that you just showed us, what would I see? And do you usually do that as a part of your feedback loop?
Exactly what you said there, that mutation testing is what gives us the confidence that the unit tests we're writing are not just giving us coverage, but are giving us coverage that's valuable, that can catch regressions. So flavors of mutation testing that we use as part of the feedback loop. And just to remind everyone, you get coverage when the method is called, not on the assertion. So we're all about delivering not just the coverage, but as you say,
right, because
good assertions that can actually
come up with 100% coverage for an arbitrary piece of code. That
you'd be amazed how many people have seen unit tests with no assertions, great coverage, can't actually catch anything.
Thank you.
I have two questions. The first one is, you said that the tool looks for 100% coverage. How does it handle the case where that's impossible due to dead code?
Due to dead code?
Yeah.
Right. So number one is we obviously want 100% coverage. We're willing to spend a certain amount of time to try to get there. 100% coverage, is itself not particularly valuable. You get to diminishing returns on that. So number one is there is a point where we do just stop and we say we can't create coverage for this code anymore. If the code is dead, if it's a dead private method, for example, then we can't even attempt to because we can't even see the method. If it's dead, but there's a public method in front of it that's calling it, yeah, we will still try, and we can still write a unit test for that dead code. One of the things that you may have very quickly seen at the end is we give you some information about what we discovered when we were writing tests. So that's where we can tell you things like the code is not testable, it's not accessible, and all these.
Okay. And the other thing is when a human writes the unit test, you have the chance of finding something that's wrong with the code. With this approach, it's pure regression. What do you say to people who are worried about that?
So when humans write unit tests, if they're writing, sorry, you mean before writing unit tests before they write the code?
Ideally, but after too, sometimes you find things because you're essentially writing the same thing in a different way, and you express the requirement and find out your code doesn't exactly do what you wanted.
Definitely. So the unit tests that we write are the unit tests that tell you what your code actually does. So it's like having me sat next to you writing your unit test and going, hey, no, that is the behavior of your code. Whether you think it or not, this is what your code is doing. So yeah, you're still able to use the unit test to determine whether your behavior is correct or
not. So on that example you showed, there were it generated 4 unit tests.
Yep.
Who decided which 4? Was that the software did it, or because I can think of like 5 more leading and trailing spaces, for example.
Sure. So number one is we are trying to get to as much coverage as possible. So we keep going. So the reason there's 4 is because we kept going and we kept discovering that we still didn't have enough coverage.
When you say we,
sorry, the application, the reinforcement learning engine, the reinforcement learning, it hadn't got full coverage for that method.
You're already mistaking it for a person, you know.
It is a person. So because the model hadn't got to 100% coverage, there are therefore more tests that we can get to. So it produced 4 unit tests because we hadn't got all the coverage.
Look, I just want to make sure I get in some other. Yeah.
So I understand. It's going to run some tests. I'm going to make some changes in my code, and it's going to check whether my changes have changed the results of the test.
You're going to check whether that is correct, though.
Now, how is it going to catch fundamental logic errors, whether I've covered corner cases, etc.? So
if the model writes the unit test before you've written your, you've got some existing code. We've written a bunch of unit tests that describe what that code does. Number one, if it's missed a corner case, that's because you've not described that corner case in your validation. So the lack of a unit test is telling you that there's a lack of a behavior in your code. So the way that you catch that corner case, or the lack of a unit test for the corner case, is by looking at your code and saying, well, my code doesn't validate that corner case, otherwise there'd be a unit test to it. Corner cases are just another pathway through that code. So if you've got a corner case that your code deals with, like an error handling, so there's for example, trading spaces is an error, your code should handle that, and we will therefore write a unit test. If you've described it in your code, so the regression model has no concept of corner cases. A corner case is just another behavior of your code. It's not looking inside the method. It's running the method. It's actually running your code. So if you that's what we're doing when we're shooting the hoops, is we're trying to understand what sets of parameters are required to call that method to trigger all of the code. And if you have a corner case, that your code has got a try catch block for, we just see that as more code that needs covering, and we will write a unit test. The lack of that unit test tells you that you've not validated for that. You actually need to change your code to add that validation in for that calling. So it takes clues from things like method names and data types, etc. It is input. It will still it will have fewer clues, but the code will still do the same thing, because fundamentally, when it's turned into bytecode, it's still the same bytecode that we see, regardless of the name. So we have fewer clues, but we still see the same code.
Yeah, I'm sorry, we have to wrap on the first speaker. Are you gonna stick around for a while, or gonna?
Yeah, no,
Okay.
I'm
If you want to follow up with your
sure.
question. So thanks again, Matt.
Thank you. Cheers.
So as Brian is setting up, I failed to say something before. I wanted to thank Bank of New York Mellon for allowing us to meet here. So thank you, Bank of New York Mellon. And of course, to thank Gradle for the pizza and the sodas. Thank you, Gradle. So if you want to get your last slice before Brian, now's a quick time to. Okay. I think there's only 2 pies left.
There's also 3 Java files.
What are they?
Java files from the 2050.
So if you want to hold one of those up,
the clues to guide that.
Luggage tags, and I think we have code.
so there's luggage tags. You just take one of the luggage tags.
We're actually
Take more than one of the luggage tags.
draw your picture.
Pass them around. Yeah, hopefully everybody here has tried some of these large language models. Has everybody tried like ChatGPT and Bard and Anthropic and everything? Make sure you do, because your career depends on it. Because these are tools that developers will be using to accelerate development. If you don't know them, you're going to be left behind. So make sure you learn them.
We have a model.
Do a quick
We'll
intro.
answer after this.
So Brian Demers, everybody knows Brian. He's a Java champion. There's only 300 Java champions on the planet, right? 350. Is there 500 now? Wow.
Yeah, 400 years.
Wow. Out of what, 8 million Java developers? Okay. So Brian is a developer advocate at Gradle. And he's everybody knows Brian. He's open source, doing a lot of contributing to open source projects. He's he's writing code, he's writing tutorials, blogs, and answering questions, which is a very, very cool thing. And Brian has a passion for fast builds and automation. And as a separate thing, away from tech geekdom, like all of us, there's always something interesting. Like I was telling Barry before, when we had talked to Brian Getz, everyone knows Brian Getz, he has a little secret, and he's a cat lover, and he's really into cats. Brian can be found playing board games, and he's also a beekeeper. Interesting.
Yeah. Oh, I forgot about that part. All right. Sure. Hopefully.
Not that I can see.
No, because I didn't click
There
the
you
button. Always click the button. All right. Hopefully that's good. All right. So today I'm going to talk about breeding 10x developers. And I'm going to talk about why I hate the term 10x developers, but not to give too much away. Thanks, Frank, for introducing me already. So the other thing I like to say about myself is everyone looks at kind of the types of software that I've looked at. It looks a little weird. I've done a lot of build tooling, a lot of security work, so application security, protocols, OAuth, that type of thing. And those seem like opposite ends of the spectrum, right? And then you realize your build connects to the internet or intranet, and your build clients are typically authenticating, right? So that's how I got involved in both those worlds. I was working on build tools, and then you need to talk to a server.
You have 2 mics?
Do I? I don't think so. This is my remote.
Yeah.
Did you lose a mic?
Yeah.
We lost the mic. Oh. Awesome. Yeah, so I really like builds. I've liked builds for a long time. It's kind of that's my nerdy niche. And then, as Frank mentioned, I'm a beekeeper. So I live in New Hampshire. I drove down on Tuesday, talked at the Garden State Jug. Some of this talk was the same. I know at least a couple of you. There are some different nuggets in here, and it's a different angle. But all right, so I'm going to start the same way though. So let's start with a little game. Right? Everyone's either going to laugh or hate me, one or the other. So raise your hand if you're a fan of tabs. Exactly. Okay, spaces. All right. I'm liking this crowd. So here's the real test though. So dogs. Okay, and cats. Ooh, I think cats have it, but New Jersey there's lots of New Jersey lovers and lots of cat lovers in New Jersey. If I can say that right. So anyways, this is my dog Zemo. He's like 2. He's a big dog. He's like 100 pounds or so. And this is just some random cat photo because I'm allergic to cats and I don't have one. All right, so here's another one. So you're all right. All right, hold on. So raise your hand for a Gradle build tool. Okay, and raise your hand for Maven. All right. So if you were paying attention to my bio slides, Maven was prominently featured. All right, so I'm actually a big Maven fan. I know very little about Gradle build tool. So why do I work here or work at Gradle? So Gradle, the company, all right, we have 2 products. So this talk isn't about Gradle, but it's this elephant in the room that I want to clear up. So Gradle, the company who I work for, created Gradle build tool. And Gradle build tool is typically what we think of whenever we hear the term Gradle, right? But we also have this product, Velocity. It's all about making your builds faster. And that works with Gradle build tool, Maven, Bazel, SPT. So it's a long way of saying we don't care which build tool you're using as long as you're productive. All right, enough of that. Let's get into it. So as I mentioned a few minutes ago, I hate this term. I hate the term 10x developer. Okay, I think it's a myth, much like these things, right? But much like these creatures, there's a kernel of truth in there somewhere. Okay, so the unicorn was likely a rhinoceros. Someone saw a rhino and thought that was a unicorn. I don't know. Centaurs, the best I could find about centaurs was non-horseback riding culture. Saw someone riding a horse for the first time. I don't know how accurate that is, but that's what Wikipedia says is accurate anyway. El Cupachabre was actually, from my research, my extensive internet research, says it's the 1995 movie Species. Anyone seen that? Yeah, like 3 of us. Yeah. Okay. So I remember watching it as a kid, and I didn't think that would spawn off that. I could not find anything from the Yetis. Does anyone know any of the original history of the Yeti or Bigfoot? Come find me afterwards. Maybe that one's real. I don't know. But the 10 right? But the 10x developer, I think, can trace its origins back to a study from the 80s. So you can scan this QR code and read the blurb of the study. I'll have all of these links at the end in the slides and a link to this talk and everything at the end. So you don't have to scan, but you can absolutely do that. So anyway, so there was a study called the Coding War Games. So in 1977, Tom DeMarco and Timothy Lister created a study called Coding War Games, right? So their goal was to come up with to figure out what the best and worst traits of software developers were. So what they did is they would take 2 developers from a bunch of different companies and have them compete basically against each other. everybody was working individually. So even the people working at the same company were competing against each other. And over the course of between 84 and 86, they had over 600 developers from about 100 different companies. So everybody was given the same project. It was a medium-sized project. They had to spec it out, design it, build it, test it, and then submit it at the end. All these developers were using their own workspaces, their computers, the languages they were most familiar with, and the results were surprising. All right, so this, like I said, this is probably where this origin of the 10x myth came from. The best developers outperform the worst by a factor of 10. Right, but before we move on, there's some non-factors here. So this is interesting. So the language they chose didn't matter, as long as you weren't picking assembly, right? we saw that on the screen. I don't know if anyone's ever done any assembly in their career, but okay, yeah, a couple of us, yeah, it's not a productivity language, okay? But as long as you aren't using assembly, you're about as effective, as efficient as the next person. Developers with 2 years of experience were about as effective as someone with 10. Now, you really started falling off the curve once you hit around 6 months, but I don't know if anybody of you remembers the first, year or two of your career. You're learning a lot just about how to work in this industry. So that's not too super surprising. The developers who finished fastest had the fewest bugs. So they had some sort of standardized testing framework that they ran everyone's entries through, but that's interesting all by itself. The fastest developers also had the fewest bugs. The top performers, so the people who did the best, were only making about 10% more than the people who did the worst. Now that's horrible, right? So if you're doing 10 times as productive as someone else and you're only making 10% more, but that's I'll leave the paychecks discussion for somebody else. All right, so let's talk about what actually did matter though. Okay, so the difference between the people at the same company, remember they weren't working together, but they were working likely in the same type of environment, was about 20%. So when factored in with everybody else, right, a 10 to 1 versus this 20%, the 20% is not statistically significant. So basically, the best organizations, so ranking organizations against each other, the best organizations did 11.1 times better than the worst. Okay, so organizations are starting to clump together here. So the idea here is you're more likely to work similar to your coworker than you are somebody else. And we can probably think about some reasons for this. So great companies attract great talent, right? If you work at a company and you're great and you know some great people, you're going to try to bring them in. The same is also probably true. There's some companies that are not doing so well. So this means our corporate culture and our corporate environment have a lot to do with how we work. Okay, so this may seem obvious, especially coming off the pandemic, but let's look at some of this data. Remember, this is from the mid 80s, but I still think this stuff is very relevant today. Okay, so I can't point to this. I don't think my laser pointer, and anyone online can't see me anyway. So hopefully you can see what I'm talking about here. So the developers who performed the best generally had more space, so more space to work. They had quieter space, right? So software development is a focused effort, right? You can't be interrupted all the time or you're not going to get anything done. So that goes hand in hand with a private space, right? And they can mute distractions. Anyone working at a company that does not allow them to mute distractions? Hopefully nobody. I know I've talked to a few folks that can't, and they as soon as they get an email, they need to respond. As soon as they get a Slack message, they need to respond. You are not going to get any work done if you work like that. I can't imagine working someplace like that. Now, if I was on call or something, that's a different story, but I haven't been on call in a number of years. All right, so anyway, so all of this may be obvious to us as we've lived through the pandemic, right? People have worked from home. Hopefully you've had a little bit of dedicated space. Maybe not. Some of you may have been working in your kitchens with little kids running around and you were less productive, but this is still the same data point we're talking about, right? Okay, so this is a long way of saying all of this. It all comes down to developer experience, right? So 10x organizations are manufactured, they're not born. So we really need to work at this. So we need to pay attention to developer experiences, removing impediments, focus on developer joy. Has anyone heard that term, developer joy? Okay, a couple of us. All right. I'll come back to that in a few minutes. All right. So has anyone heard of the space framework? One, all right. Okay, so measuring productivity is hard. How do you folks measure productivity? Does anyone measure story points or lines of code or, I don't know, some arbitrary metric? A couple folks. Yeah. Okay. So we're doing something. You got to try to do something, right? So the space framework tries to fix that. So this came out of Microsoft and the University of Victoria. So they realized that a single metric just wasn't going to do. They needed to create multiple metrics and then aggregate them together. So I'll go down the list here. So satisfaction and well-being, that's your happiness, your stress, your purpose for your job, all of those types of things. The performance, so that's how well you're meeting deadlines. Activity, that's writing code. That's typically what we think about. Communication and collaboration, and efficiency and flow. So there is not a single way to get this data. So that's a bit of a problem. You can't standardize it. But you can ask your developers and your workers a series of questions, and then you can kind of categorize them and see how you're doing. If you do that, your developers and your managers are going to respond differently. That's probably not a big surprise. But managers are typically going to define productivity in terms of performance. Remember, that's meeting their deadlines, right? And developers, we're mostly concerned with writing code. So that's what we think about when we talk about productivity. The sad thing is, you see the satisfaction number? Single digits. Nobody's very satisfied with their job, and that's not great. So coming back to being happy about your job, I know that when I'm happy, when I'm doing something, I'm more productive. Even if I can't measure that better productivity, I feel like I'm better. I'm more engaged. My attention span is held within my code. I'm excited to share that with my coworkers or a user group, right? But I can just stay focused. So it's a long way of saying all of us need to be better aligned at what we're looking for. Reporting dates up the food chain probably isn't the best thing for productivity. Okay, so all of these things we've been doing, right? DevOps, 12-factor, Agile, these are great. But as soon as we do one thing, we uncover another bottleneck. So Agile removed the pain of waterfall. So I remember early in my career, I spent weeks and months doing requirements docs. Anyone have stories like that? Some of us, yeah. And now we're kind of, do our requirements docs a little bit at a time. So hopefully nobody's still spending weeks and months, but I don't know. I'm sure there's some of us out there. All right. So 12-factor was all about making our applications easy to deploy. That's great. DevOps, now we have infrastructure as code. We're treating environments as cattle instead of pets. Awesome, right? But the pains that we're going through are still there, right? Developers still deal with a lot of pain every day. So 10x organizations really need to think about these things and reducing build times and reducing feedback cycles. And really just improving the reliability of your tests and your builds. So really that's what developer productivity engineering is all about. So DPE is a engineering practice that uses straightforward techniques to foster developer success and happiness. You can tell I've tried to say that line like 6 times, right? Sorry. So anyway, so success and happiness, right? If you give me the option for success and happiness, I'm going to pick that option every time, right? So DPE emphasizes a few key things. So fast feedback cycles, right? We want our builds to be fast. Tool chain reliability. We don't want flakiness. So I'm going to talk about flaky tests a little bit here and there, but a flaky test is a test that will pass 1 minute. You run it again and maybe it fails, right? Flaky test, flaky build, those things are evil. I'll come back to that. And actionable data. We need actionable data from our builds and our productivity to then feed back into our system to make us more productive. So basically you want to put the developer at the forefront, optimize everything we can, build tools, CI times, all of that stuff. All right. So software development is a craft, right? It's a creative activity. Does anyone remember the first Hello World application they wrote? Some of us, yeah. So I think my memory's a little fuzzy in this, but I really think it was messing around with a Windows command prompt or DOS command prompt, right? I think I made the prompt say Brian is awesome. And then this was back in the days of shared computers, right? So my sisters were not impressed, but I'm pretty sure I made it loop infinitely, right? And then nobody was happy, but I thought it was great. But in doing so, your brain gets a sudden hit of dopamine, right? You do something, you get instant feedback, right? That feels great. Maybe something fails. It's still right away, right? And then you can try it again, do something, and then you'll get that hit of dopamine again. So fast forward to today, right? If we put these kids in front of kind of modern software development, do you think they'd be happy? Right? No, these kids are not going to be happy, right? They're not going to be happy if they have to sit there and wait 20 minutes for their build, right? Long builds, flaky tests, all those things. We would not expect them to do that. Why do we expect us to put up with it, right? So we really deserve better than this. All right, so look at this fictitious calendar. I'm going to wave a magic wand. I'm going to remove all your meetings. Okay, great. No more meetings. Your day is still going to be frustrating, right? This is unfortunate. So let's pretend I'm going to work on a feature for a small feature in my project. I think it's going to take a couple hours to fix or complete, right? So I get into it. I'm in my IDE, pretty focused. I'm in the flow. I'm in the zone, you know. My brain is happy. After a couple hours of working through my IDE, I think I've got it all worked out. Maybe I've run some tests, but I'm going to start a full build and then wait for that before I push it off to CI, because I'm a good developer, right? So I do that and it fails. Hopefully it fails right away, but I'm still in the zone if it fails right away, right? I'm still focused on what I'm doing. Maybe a test passed, a test failed, and I fix it, I get back to it, awesome. But sometimes these things fail for no reason, or they fail 20 minutes from now, right? And that's frustrating. These things take me out of the zone. Maybe I don't have enough data to fix the issue, right? So I have to ask my teammates. Maybe I'm frustrated. I go to lunch. I walk my dog, whatever it is. I come back. Maybe my teammate sent me a Slack message. Here's how to fix the problem, Brian. Awesome. So I get back into it. I fix the issue. I work on that for a while. And then I go through the same cycle again, right? I kick off the local build. I wait for it. Then I submit this thing to our CI server, maybe a pull request. And nobody on my team is going to review my code until that thing goes green on CI, right? So I'm sitting there waiting a little longer, but CI fails, right? Worked on my machine. I ran the full build, but why does CI fail, right? It works on my machine, quote unquote. You know, so I have no idea if this build failure is related to my change or not. So I spend the next hour digging into it. I have no idea what the issue is. Right. And at the end of the day, this issue I thought was going to take 2 hours in the morning. And now I'm trying to get home. So anyway, it's a fictitious story, right? But we all have examples like this in our careers and our lives. We really owe ourselves a better experience in this. Now, getting back to long build times, right? Everyone loves this comic. Hopefully everyone's seen this comic, right? Does anyone actually ever sword fight font in the office? No, okay, but you've played other games, ping pong or foosball or any of those things, right? Does anyone have an hour-long build or more here? A couple of folks, yep, yeah. Well, I bet yours is probably friggin' days or whatever. We'll talk about that later. All right, who's got builds longer than a half an hour? A few of us, yeah, okay. Who has builds under 2 minutes with tests? Yeah, okay, awesome. Okay, awesome. So that's great. But most of us are dealing with a lot of these pains, right? So I think once your build gets much longer, then honestly, probably 45 seconds, you know, but I'm going to use the 2-minute mark, then you're going to have to go do something else while that thing is running, right? So if I just stood here for 2 minutes, how long would it take you to pull out your phone? Right? Right? Like 20 seconds, maybe 30 if you're nice to me. I don't know. So here's some ways that you can fix and speed up your builds, and hopefully not have to sit and play Angry Birds, or I don't know what the current game is. Sorry. While you're waiting for your builds. All right. So first thing is first, build cache. Has anyone heard of a build cache? Few folks? Awesome. Okay, a lot of folks. So in our applications, if you were to build an application today, right, and it's slow, one of the first tools you go to is a cache, right? So we really need to start thinking about our build the same way we think about our applications. It's slow, you add a cache. I'll explain a little more about build caching in a minute here. So next up is predictive test selection. I actually gonna move this order around. But predictive test selection is basically all about reducing work. This is a complicated one, and I'll come back to that in a future slide. This one should be a little more obvious, right? So test distribution. So in order to make tests faster, I can distribute them across a bunch of nodes. Now, the same thing we do with our applications, we distribute the work across a bunch of nodes. We need to start thinking about our applications, our builds the same way we do our applications. Now, does anyone have an application in production that you do not monitor? Does anyone have one they don't want to raise their hand? Yeah, so you've probably seen them before, but it's very common to monitor your applications in production. You want to monitor, response times, all these things, right? Why aren't we doing these things for our builds? Right? Why aren't we monitoring our builds? We really need to watch for trends, those types of things to make sure we're productive. All right, so let's go through all these topics. So build caching, again, some folks have heard of this. I think this is one of the easiest way to speed up your builds. And you could go back, Gradle has a build cache, Maven now has a build cache. You could turn these on right now and get a lot of benefit out of this. So a build cache, just to be clear, a build cache is not the same as a dependency cache. So many of us have like an Artifactory or Nexus instance running on our corporate network. You download artifacts, they're cached in your network, and then again on your local machine in your home directory, right? Maven users, it's your M2 home directory, or M2 home / repository, a whole bunch of jars in there. Build caching is different. So build cache is going to cache the individual goals or tasks, and these things are typically the CPU intensive things, compilation and testing. Those are the big ones. Those are typically where your build spends the most time. So Maven has a cache. It's an extension. DevVelocity also has a Maven cache. There's some nuances, differences between the two, but basically our product works with all of these caches. We don't care which one you use. There's two ways to use a cache. So local cache. So if I run a build, I'm going to cache things locally for me. And if I want my whole team to take advantage of a cache, I would use a remote cache. My CI server would populate a cache, and then my build would automatically download those cache entries. Okay, so from a high level, let's look at compilation. Okay, so Gradle task or Maven goal has a set of inputs. Right, for a given set of inputs, you would expect the exact same set of outputs. So for compilation, we have source files, we have dependencies, compiler version, the compiler arguments, a whole bunch of those things, right? And for that, you would expect the same set of outputs, usually a set of class files, right? They should, same inputs, same outputs. That's critical because you can't really cache something if either one of those is unstable, right? Same way with your application. You can't have an application that caches something if your inputs and outputs are not stable. For test runs, you would have a test report or maybe coverage data, right? You can cache those things. So what you do is you take those inputs and you just hash them. That gives you a string. That's a cache key. You associate that key with basically a zip file of all the output. So in the case of compilation, you zip up your class files. You store them typically in your home directory for later use. So if you do a clean build, you can just unzip that file. And this will save you a lot of time. All right, has anyone heard of reproducible builds? Awesome. All right, so this is my favorite thing since sliced bread, okay? So reproducible builds, if you haven't heard about it, is a set of practices that makes it possible to build your software multiple times and get the same output byte for byte, right? So same inputs, same outputs. Hopefully you see where I'm going with this. So this is typically seen from a good move for security, right? It allows us to build our software and verify artifacts. So if I build my code and you build that same code and we get the same artifacts, you know that I didn't inject anything malicious in my code, and you know, and I know you didn't. Now, intentionally or unintentionally, Maybe I have malware on my machine. Maybe there's malware on your machine, whatever it is. But now we're reasonably assured that we don't. So the interesting side effect, right, of all of this is it makes your build highly cacheable. So now we have a security practice that makes you more productive. Does anyone have a security practice that makes you more productive? Right? No, it's that I'm a security guy, right? I love that stuff, but it is, I've never heard anyone say, yep, this process will make things faster. Nobody says that, right? So reproducible builds has that potential. Okay, so enough about that. So test distribution. So our builds, where they're cached, they're fast, but I'm going to make changes as I'm working on my code, and I'm going to have to run my tests. So I'm going to distribute them across a bunch of nodes. We've seen cases where oftentimes 90% of your build time is testing. And I'm guessing many of you, maybe not you, maybe not Matt over here, but many of us that have these hour-long builds, it's probably mostly testing, probably integration testing, right? So anyway, so you have an autoscaler. Multiple companies have different techniques for this, but this is the basic premise. You have an autoscaler on Kubernetes, and you spin up a bunch of agents, and you use them as needed. So that means my build on my laptop can then farm out my tests to these agents. My CI system can do the same thing. And my coworkers, we can all use the same set of workers, right? So now I'm no longer limited to the processing power of my laptop. I will say, if you are not already running parallel builds, so the Maven and Gradle both have parallel building options. If you are not already using them, you should use them now. There's also options to run your tests in parallel. It's not something you can just enable. Running them on different machines helps a little bit with that, but I think it's still worth going through the effort of getting your tests to make sure they work and run in parallel. So if everything's using port 8080, your tests probably aren't going to run in parallel very well, right? But anyway, so now all of your test data, everything should actually, your build, your test results, your coverage data, all should come back to your laptop. So your build should look like one build and not 1,000 little builds. Netflix did this. They were able to take an hour-long build and test cycle and get it down to under 5 minutes. So I'll have a link to this at the end. So predictive test selection is this one that I kind of waved my hands around. So this is an interesting one, and it took me a really long time to wrap my head around it. So the premise here is, if I change a source file, chances are good I don't need to run my entire test suite, right? If I do run the entire test suite, I'm kind of wasting my time and CPU cycles. So Facebook published this paper, or now they're Meta, but when they wrote this paper, they were Facebook. You can read about this here. Again, I'll have a link. But the idea here is they were not happy with the conventional approach. So if you think of your code changes, the red diamonds across the bottom, and then you just try to find all your dependencies, right? A graph of all the code that's touched by those changes, and you run their test 1, 2, 3, 4 across the top, right? So that's kind of what we do now. This paper describes a machine learning model that takes into account a lot of different inputs. So file names, extensions, past test runs, all of this data, and uses the model to predict how likely your test is to pass, with your change. If it's likely to pass with your change, you don't need to run it. Okay, so hopefully you're taken aback a little bit by that. I don't need to run my tests, right? So this comes with caveats here. Okay, you can use this sometimes. So I can use this for local development, right? That'll speed up my development cycle. I could use this for a pre-merge pull request or pre-merge pull request builds. So remember, that's the build that your teammates are not going to look at your pull request until that thing goes green. So now those things are fast. And my CI pre-merge builds can be fast. And then once I merge the things into our main line, we can run all of the tests, right? Or just the rest of the tests. So this will make your builds much, much faster. So build scans. So you've introduced all these things, right? Now your builds are super fast. You still need an accurate, an easy way to troubleshoot issues, right? So I don't care who you are, builds are complicated, right? They're hard to debug if you don't have enough data. data. So that's what build scans are. You go to scans.gradle.com, you can try them out. Our paid product actually has a way you can diff builds. So if you have a working build and a failing build, you can compare them and figure out all the differences, whether it's dependencies, OS versions, Java versions, you name it, you can figure out the difference. Okay, so this is great, right? So we have fast builds, we can troubleshoot them. But if you're not paying attention to your builds, not monitoring them, you're going to start running into problems. So if I sent you a pull request right now that added 5, maybe 10 minutes to your build, you're going to notice, right? But that's not really what happens. What happens is it's 5 seconds here, it's 10 seconds there, and eventually we're going to get to that 5 or 10 minute mark, right? Is anyone working on a code base that's shrinking? No, right? Nobody is. So we really need to pay attention to these things and watch for trends. You know, if you have somebody that moves to a different office, maybe their build times are slower there, right? So you really need to monitor for them. Maybe it's just a networking issue. Maybe that office needs a bigger pipe. Maybe it's missing some infrastructure. Maybe that person is still connecting across the country to their old office's infrastructure. Without some kind of data, you don't really know this stuff, right? There could be an issue that's, you know, one person complains about. I'm going to complain about a build issue, but my 19 coworkers are not, right? They still have the same issue, but they're not just saying anything. They're used to it, right? So we need data to start paying attention to this stuff. Is anyone actually tracking build times? Like, you know accurately how long your builds are? Awesome. Some of us are. So obviously we have a product that does this, but you can do this on your own, right? You can write a Maven extension or a Gradle plugin to dump your build times into a database and start tracking this stuff. I would absolutely recommend that. So this is often a question that we get, right? Is your build time fast enough? And everyone's like, yeah, I think it's fast enough. But really, is the build time as fast as it can be? Is really what you want to start asking. So obviously, we think DPE sparks joy, right? I think you will too. Definitely check this out a little more. I'm running out of time, so I'm going to go through this really quick here. You're going to track failure rates. I love to talk about flaky tests, but for some reason I put it at the end of my talk, so that's unfortunate. I have a whole talk on this topic, and I like to talk about how testing gives us confidence, and flaky tests erode that confidence. Okay, so the question here is, what is the first thing you do when your CI build fails? Do you look at the log, or do you click the rerun button? Everybody clicks the rerun button, okay? So that means you do not trust your build, you don't have any confidence in it. So if you have a 20-minute build or a 40-minute build, and you click the rerun button, now it's a 40-minute build or an 80-minute build, right? It's a big waste of time. So you really need to be tracking. Yeah, just delete the test. Just generate them. So we really need to be tracking flaky tests, right? I don't care what you do, dashboards, wiki pages, email threads. I've worked at places where they've sent emails every other day, like, don't worry about test XYZ, right? So you really need a way of paying attention to them. Gradle has what we call flaky test days. So what we do at the end of a release cycle, if we have a bunch of flaky tests, the whole engineering team will get together, and they will virtually, and they will fix the flaky test. So they have a list, and they go down the list to, you know, what's affecting us the most. And this does two things. This stabilizes our build, which is great all by itself, but it also instills that, you know, it's not okay to have flaky tests, right? It's not something we want to allow. So it trains everyone to not look past them. So I'll come back to you 1 minute. I'm almost done here. So I think DPE is becoming a standardized practice. I hope you will too. So being productive and happier is this perfect pairing in my book. So there's a couple ways you can learn more about this topic. So if you scan this QR code, you're going to get the link to my slides, a link to the live stream. You're here, so you may not need that part, but it'll have all the links that I talked about as well. And there's two ways that you can get free stuff from Gradle. So we have a build speed challenge. So you add caching to a build an example project. It usually should take you about 5 minutes. And we'll send you a swag box. We'll just mail it right to your house. I think it usually has a t-shirt, socks, stickers. I've heard rumors that it might even contain a mug sometimes. I don't know. Don't quote me on that one. And then we have the system called Influitive. So Influitive is kind of a gamified learning. So this is what you see here pictured on the left. So hats, t-shirts, Lego. I'm a big Lego fan. But you can read a chapter of a book and answer a question. You get points. There's some light social stuff you can do, or some heavy stuff. Do a conference talk, right? We'll give you a bunch of points. So anyway, you turn those points into stuff. It's really easy to get enough points for a t-shirt. But if you scan that, you can get some stuff. All right, so I don't know how much time we have, but
we have 2 quick questions. We have
2 quick questions. All right. So I know there's a question over there.
When talking about the test, you're talking about system integration test or just unit tests or both?
Tests in general. So I have a whole rant about how I think most people do unit tests, but they're actually integration tests. So just tests. Anybody else? I can answer questions on the way out too. Oh,
Someone said that they are doing their builds in like few minutes, under 2 minutes or something. Like, we would like to know more about that.
Fast tests. I bet you that's the answer. Either no tests or fast tests. Hopefully it's fast tests. Yeah. Yep. Awesome. All right, everyone. Thank you.
Thank you, Brian. Thank you, Matt.